The cosmos holds worlds stranger than any fiction. For most of human history, our solar system defined the very idea of a planet. But modern telescopes have ripped open that narrow view, revealing a staggering truth. Thousands of exoplanets, planets orbiting distant stars, fill our galaxy. They are not mere copies of the worlds we know. They are a menagerie of the impossible, a testament to nature's boundless creativity. By the end of this journey, you will have explored 25 of the most bizarre recent discoveries, each one rewriting the rules of planetary science. We will visit a planet where it rains molten iron and another darker than coal. We will question if a world made of diamond could exist and what life might cling to in a permanent twilight zone. What do you believe is the ultimate limit to how strange a planet can be? Our journey begins with a world of unimaginable wealth and blistering fury. Astronomers call it 55 Cancri E, but you might know it by a more glittering name, the Diamond Planet. This is not a gentle, Earth-like world. It is a super-Earth, a planet several times more massive than our own, locked in a death spiral around its sun-like star. Its orbit is so incredibly tight that a single year there passes in just 18 hours. Imagine celebrating your birthday every single Earth day and then some. This proximity creates a hellscape. The daytime surface temperature soars to nearly 4,300 degrees Celsius, hot enough to vaporize iron and melt steel instantly. Any traditional rocky surface, like the silicate rocks of Earth, would simply not survive here. So what is this planet made of? This is where the mystery turns to treasure. By carefully measuring the planet's mass and size, scientists calculated its density. It is surprisingly heavy for its volume, but not heavy enough to be a rocky world like our own. The data pointed to a startling composition: carbon, vast amounts of it. Under the immense pressure and searing heat of this world's interior, carbon crystallizes. The theoretical models suggest a planetary core of solid diamond, possibly thousands of miles thick, overlain by a layer of graphite and perhaps even seas of tar. The very surface could be a cracked, sparkling crust of diamond and graphite, glowing under the relentless glare of its nearby star. While we cannot see this diamond crust directly, studies of the thin, vaporized atmosphere hint at carbon-rich gases, supporting the incredible theory. This is a world where the bedrock itself is a gemstone, a monument to cosmic alchemy where common elements transform into a king's ransom under the most extreme conditions imaginable. Yet the diamond world's scorching permanence is just one form of cosmic stillness. Shift your gaze 4.2 light-years away to our very next-door neighbor in the stars, and you will find a different kind of frozen tableau. Orbiting Proxima Centauri, the closest star to our Sun, is a world named Proxima Centauri b. It is a rocky planet, roughly the same size as Earth, and it sits within its star's so-called habitable zone, where temperatures could theoretically allow for liquid water. This discovery sparked immediate excitement, a potential Earth twin right on our cosmic doorstep. But the reality is far stranger and more haunting than a simple copy of our world. Proxima Centauri is a red dwarf, a small, cool, and tempestuous star. Because the planet must orbit very closely to this faint sun to stay warm, it has become tidally locked. This means the same hemisphere forever faces the star, while the other is condemned to eternal night. The planet does not spin as Earth does. Imagine holding a ball on a string, always keeping the same side toward a lamp. That is Proxima Centauri b. The result is a world split into two absolute kingdoms. The day side is a scorched, sun-blasted desert, perpetually cooked by the red glow of its star. The night side is a deep frozen wasteland where any atmosphere would likely collapse into a permanent ice sheet. From a distance, this stark division gives the planet an eerie appearance, like a giant eyeball staring out into the void. But between these two extremes lies a sliver of possibility, a ring of twilight known as the Terminator line. Here, along this perpetual dusk or dawn, conditions might be just right. The star would forever sit low on the horizon, casting long, soft shadows. Temperatures could be mild, neither boiling nor freezing. If water exists on this world, it could flow here. If an atmosphere persists, winds might howl from the hot side to the cold, circulating nutrients and energy. This narrow ribbon, this borderland between fire and ice, is where astrobiologists dream of finding signs of life. Could strange, hardy organisms cling to this twilight zone, following the sun as it hangs motionless in the sky? The very idea challenges our Earth-centric view of habitability, suggesting that life, if it exists, may thrive not on whole worlds but in their most precarious margins. From the frozen twilight of a tidally locked world, we now venture to a planet that seems to defy the very concept of solidity. Meet WASP 107b, a world so light and airy it has earned the nickname the Cotton Candy Planet. Orbiting its star every 5.7 days, this is a gas giant, but one of a profoundly strange breed. It is nearly the size of Jupiter, yet when scientists measured its gravitational pull, they discovered something astonishing. It possesses only about 1/10 of Jupiter's mass. You could fit 10 of these planets into the mass of a single Jupiter. This gives WASP 107b an almost impossibly low density. If you could find an ocean large enough, this entire planet would float. Its atmosphere is not a thin layer over a solid surface. It is a vast, puffed-up envelope of hydrogen and helium that extends for thousands of miles, giving the planet a soft, bloated appearance more like a celestial cloud than a traditional world. How does such a fluffy giant even form? The leading theory paints a picture of a dramatic migration. Astronomers believe this world likely began its life much farther out from its star, in the colder regions where ice and rock slowly clumped together. There it could have built a substantial rocky core, perhaps 10 times the mass of Earth. This hefty core then began to pull in the lightweight hydrogen and helium gas from the surrounding stellar nursery, swelling into a giant. But then something happened. Gravitational interactions with other bodies or the disk of material it was born from may have sent this fledgling planet spiraling inward toward its star. As it migrated into a much tighter, hotter orbit, the intense stellar radiation began to cook its atmosphere from the outside in. The heat pumped energy into the gases, causing them to expand dramatically, like a balloon left in the sun. This relentless baking gave the planet its extraordinary, fluffy character, inflating its atmosphere to a size that completely mismatches its weight. This cosmic confection poses a serious challenge to our models of how planets are built. A core massive enough to attract that much gas so quickly, yet a final planet so lightweight pushes at the edges of our understanding. It suggests formation pathways we are only beginning to map, where planets can be sculpted not just by where they are born, but by the turbulent journeys they take afterward. WASP 107b is a reminder that planets are not static sculptures. They are dynamic entities, shaped and reshaped by the violence of their youth. And if a planet can be this ethereal, what other forms of delicate architecture might exist in the cosmic dark? But even the fluffy majesty of a cotton candy planet cannot prepare us for the raw, geological fury of our next destination. Meet K2141b, a world so brutally close to its star that the very concept of a solid surface becomes a fleeting dream. This is a lava world, a super-Earth orbiting so tightly that a single year lasts less than 7 hours. Imagine a planet where your entire calendar fits within a single Earth day. This proximity creates an environment of apocalyptic extremes. The planet is tidally locked, with one hemisphere permanently facing its orange dwarf sun. That dayside is a vision of pure hell, with surface temperatures soaring beyond 3,000 degrees Celsius. At that heat, rock does not just melt, it vaporizes. The ground itself boils away, creating a vast, churning ocean of molten silicate lava, hundreds of miles deep, under a sky filled with the vaporized minerals of what was once stone. This vapor rises, forming a thin, scorching atmosphere not of oxygen or nitrogen, but of sodium, silicon monoxide, and silicon dioxide, the literal breath of a vaporized crust. Here, the weather is written in stone. Powerful supersonic winds, driven by the immense temperature difference between the day and night sides, blast this mineral vapor across the terminator line into the planet's eternal darkness. On that frozen night side, which plunges to temperatures below -200 degrees Celsius, the vapor atmosphere cannot survive. The mineral particles condense out of the sky. But they do not form water droplets. Instead, they create a precipitation more suited to a demonic forge. Scientists using sophisticated climate models predict a relentless, grim weather cycle. Dense clouds of rocky silicate particles form in the freezing air, and then it begins to rain. Not water, but tiny droplets of liquid rock. Further down, this rain turns to snow, a blizzard of solidified lava flakes, drifting slowly down onto a frozen landscape of solid rock. This snow then accumulates, forming glaciers of rock that creep slowly back toward the searing dayside under their own weight, only to be vaporized once again, fueling the entire horrific cycle. This world is a colossal, self-sustaining rock furnace, a planet where the mountains are made of lava and the storms are made of the dust of its own evaporated bones. It is a stark demonstration that a planet's climate is not defined by water alone, but by whatever element is volatile enough to be lifted into the sky by its star's relentless energy. K2141b shows us that the forces of evaporation, wind, and precipitation are universal, but the materials they work with can transform a familiar process into a scene of breathtaking, terrifying alien geology. If a world can have a water cycle of stone, what other impossible meteorological dramas are waiting to be discovered in the galaxy's infinite variety? While lava worlds burn with the fury of a vaporized crust, other planets exist in a profound and perfect darkness. In the constellation Draco, a gas giant named TRS-2b orbits its sun-like star, but you would never see it coming. This world holds a singular, unsettling title. It is the darkest planet ever discovered. Imagine the blackest charcoal, the deepest space, a void of pure shadow. TRS-2b is darker still. Precise measurements from the Kepler Space Telescope revealed a shocking truth. This planet reflects less than 1% of the light that strikes it. For comparison, the blackest acrylic paint reflects about 4%. Jupiter, our solar system's familiar striped giant, reflects over 30%. TRS-2b is a cosmic black hole of a planet, a void that swallows nearly every single photon that touches its atmosphere. So what creates this profound absence of light? The planet is a hot Jupiter, orbiting blisteringly close to its star, which superheats its atmosphere to well over 1,000 degrees Celsius. At these temperatures, familiar clouds of reflective ammonia or water vapor cannot form. Instead, scientists believe the atmosphere is filled with exotic, light-hungry chemicals. Vaporized sodium and potassium could be present, elements that are exceptionally good at absorbing visible light. Another prime suspect is gaseous titanium oxide, a compound so effective at soaking up light that it is used here on Earth to make some of our darkest industrial pigments. These substances act like a celestial light trap, ensuring that any starlight penetrating the upper atmosphere is almost entirely consumed, never to bounce back into space. Yet, this absolute blackness is not the whole story. The planet's own immense internal heat, generated by the crushing gravity of its tight orbit and leftover energy from its formation, may give it a faint, eerie glow. If you could somehow stand on a platform near this world, you might not see a defined sphere, but rather a ghostly, dark red ember hanging in the black, a silhouette that radiates its own dim, infernal warmth. It is a world defined by what it lacks, an object that is paradoxically both there and not there, a massive, seething presence cloaked in a perfect, light-eating shroud. This discovery forces us to ask how many other invisible giants are hiding in plain sight, their darkness mistaken for empty space, simply because we never thought to look for a planet that gives nothing back. The profound darkness of TRES-2b speaks to a planet defined by its atmosphere, a shroud that reveals nothing. But what if an atmosphere was not a cloak but an entire world? Our journey brings us to a celestial body that blurs the line between planet and ocean, a place called GJ1214b. Discovered orbiting a small red dwarf star 48 light-years away, this world is classified as a mini-Neptune. It is larger than Earth but smaller than the ice giants of our own solar system, and for years its true nature was hidden behind a uniform, hazy veil. Observations from the Hubble Space Telescope revealed an atmosphere with no features whatsoever, no clouds, no bands, no chemical signatures peeking through. It was a smooth, blank canvas, a perfect pale orange sphere. This frustrating featurelessness was ironically the biggest clue. It told scientists that the atmosphere was not thin and clear, but incredibly thick and steamy, likely blanketed by high-altitude haze or perpetual cloud cover, preventing any glimpse of the depths below. So what lies beneath that impenetrable shroud? The planet's mass and size point to a composition drastically different from rocky worlds. It is far too light to be made mostly of rock and metal. The most compelling model suggests GJ1214b is a water world, but one that makes our oceans look like puddles. Imagine a planet with no continents, no beaches, no rocky shorelines at all. Instead, picture a global ocean so deep it defies comprehension, perhaps hundreds of miles from the top of the atmosphere to the ocean floor. But this is no placid, blue expanse. Due to the planet's proximity to its star, the surface temperature is estimated at over 200 degrees Celsius. At that heat, and under the crushing atmospheric pressure thousands of times greater than Earth's, water exists in a bizarre, supercritical state. It is neither a true liquid nor a gas, but a dense, hot fluid with properties of both, seething with immense energy. Dive deeper, and the pressure becomes so astronomical that the water molecules are squeezed into forms of exotic ice, not the frozen kind we know, but high-pressure crystalline structures like Ice 7 or Ice 10. This ice would not be cold, it could be hundreds of degrees hot, but the pressure forces the water into a solid state regardless. The entire planet, then, could be structured in layers, a steamy, thick atmosphere giving way to a global supercritical ocean, which in turn sits atop a mantle of hot, solid ice, and finally, perhaps a small rocky core at the very center. This is a world where the very idea of land is a fantasy, and the ocean is the planet itself. GJ1214b represents a whole new class of planetary object, one where the most common solvent in the universe becomes the primary building block, creating a fluid globe under a permanent, featureless twilight. If life could emerge in such a place, it would not look to the stars, for there are none to see, only an endless, pressing, hot abyss in every direction. The endless, steamy ocean of GJ1214b presents a world defined by a single, overwhelming element. But another planet takes a familiar material and transforms it into a meteorological nightmare. This is WASP-76b, an ultra-hot Jupiter where the weather forecast is written in metal, orbiting so close to its star that a year is just 1.8 Earth days. This gas giant is tidally locked in a deadly embrace. The permanent dayside is a furnace beyond comprehension, with temperatures soaring to an unimaginable 2,400 degrees Celsius. At that heat, molecules are torn apart, and metals do not simply melt, they boil. Iron, one of the most common heavy elements in the universe, vaporizes completely, turning into a shimmering, gaseous mist in the upper atmosphere. Here, the star's relentless fury creates supersonic winds howling at thousands of miles per hour. These ferocious jets act as a planetary conveyor belt, sweeping the vaporized iron from the scorching dayside across the terminator line and into the eternal night. As the iron vapor crosses into darkness, the temperature plummets by nearly 1,000 degrees. In that sudden, profound chill, the iron can no longer remain a gas. It begins to condense. First, it forms clouds, not of water, but of tiny droplets of liquid metal. Then it falls. On the night side of WASP 76b, it rains molten iron. This is not a theory or a clever model, it is an observed fact. Using the espresso spectrograph on the Very Large Telescope in Chile, astronomers did something extraordinary. They took the chemical fingerprint of the planet's atmosphere as it passed in front of its star. On the dividing line between day and night, they detected the clear, unmistakable signature of iron vapor. But when they looked at the line marking the transition from night back to day, that signature was gone. The iron had vanished from the morning sky. The only explanation that fits is a brutal, elemental cycle. The iron condenses out of the atmosphere and pours down as a burning drizzle of liquid metal. Imagine standing on a hypothetical platform in that eternal twilight, looking up into a black sky streaked with the faint, glowing trails of falling iron. You would hear no thunder, only the silent, relentless precipitation of a world's evaporated bones, solidifying in the dark and returning to the depths. WASP 76b is a giant cosmic forge, demonstrating with terrifying clarity that a planet's climate is dictated by whatever its sun can force into the sky, and what the cold dark of space can then wrench back down. The silent iron rain of WASP 76b speaks to a universe of brutal, elemental cycles. Yet another world offers a spectacle not of meteorological terror, but of celestial harmony, a vista drawn from science fiction and made real. Orbiting a pair of stars 200 light-years away is Kepler 16b, a planet forever immortalized as the real-world Tatooine. This is a circumbinary planet, a world that does not orbit a single star but two. The stars themselves are a dancing pair, a smaller, cooler orange dwarf and a still smaller red dwarf, locked in a 41-day orbital waltz around their common center of gravity. And around both of them, tracing a wide, stable path, moves the planet Kepler 16b. For decades, astronomers debated whether stable planets could even exist in such a dynamically chaotic environment. The competing gravitational pulls of two stars should, in theory, tear apart any fledgling planet or fling it into the void. The discovery of Kepler 16b in 2011 was a monumental breakthrough, a definitive proof that planets can not only form in binary systems, but find a peaceful orbit amidst the stellar dance. The planet itself is a cold giant, roughly the size of Saturn, but with a density suggesting a mix of rock and gas. Its orbit takes 229 days, and because it circles both stars, it experiences sunlight from two different sources. The view from its hypothetical moons or upper atmosphere would be unlike anything in our solar system. Two suns, one larger and orange, the other smaller and dimmer red, would chase each other across the sky in a complex, ever-changing celestial ballet. There would be single sunrises and sunsets when one star is blocked by the other, periods of double daylight, and most famously, the double sunset. As the planet rotates, an observer could witness both stars dipping below the horizon in sequence, casting long, intertwined shadows and painting the sky with dual layers of color. But this beauty comes with a price. Because the planet orbits so far out to maintain stability, it lies far beyond the system's habitable zone. The sunlight it receives is faint, leaving its cloud tops at a frigid negative 70 degrees Celsius. This is not a desert world like its fictional counterpart, but a frozen gas giant, a silent spectator to a perpetual double dawn. Kepler 16b shattered a fundamental assumption and expanded the cosmic real estate where we might look for worlds, proving that even in the gravitationally complex neighborhoods of binary stars, the universe finds a way to build planets. The silent, frozen majesty of a double sunset world stands in stark contrast to a planet that is quite literally falling apart before our eyes. 33 light-years away, a world named GJ436b is engaged in a slow, spectacular act of self-destruction. This is a hot Neptune, a gaseous world roughly the size of our own Neptune, but orbiting so close to its small, cool red dwarf star that its year is just 2.6 Earth days. The star's radiation, though faint by solar standards, is relentless at such close range, and it is baking away the planet's atmosphere. Using the Hubble Space Telescope, astronomers witnessed something extraordinary. A giant, glowing cloud of hydrogen enveloping the planet and streaming away into space, forming a colossal tail that stretches for millions of miles. GJ436b looks less like a planet and more like a giant comet, with its atmosphere being blown back by the stellar wind. This process, called hydrodynamic escape, occurs when the upper atmosphere heats up so much that the lightest gases, like hydrogen, gain enough energy to overcome the planet's gravity entirely. They do not just leak away, they flow, a river of atmosphere pouring into the void. The scale is almost incomprehensible, with the planet losing an estimated 1,000 tons of its atmosphere every single second. At that rate, scientists calculate this world may have already lost over 10% of its entire mass, and in another billion years, it could be stripped down to nothing more than a barren, rocky core. This violent evaporation offers a crucial clue to a long-standing cosmic mystery, the so-called hot Neptune desert. Astronomers have found very few Neptune-sized worlds in such blisteringly close orbits, and GJ436b shows us why they simply cannot survive there for long. They are the intermediate casualties of planetary evolution, giants that migrated too close to their stars and are now being systematically dismantled by the very suns they orbit. Adding to its strangeness, this dying world follows a bizarre path. It orbits perpendicular to its star's equator, a highly inclined, almost polar orbit that suggests a violently chaotic past, likely a gravitational showdown with another unseen planet that kicked it into this doomed close in trajectory. GJ436b is a planet in its final, dramatic act, a glowing testament to the fact that in the cosmos, even entire worlds are not permanent, but transient structures, sculpted and ultimately erased by the forces they cannot escape. The slow, fiery disintegration of a world like GJ436b reveals a possible fate for many planets, but sometimes the stripping process is so complete it leaves behind only a skeletal remnant. This brings us to TOI 849b, a cosmic anomaly so dense it defies all expectations. Discovered by the TESS satellite, this world orbits so close to its sun-like star that a year lasts a mere 18 hours. At first glance, its size seemed familiar. It is roughly the same diameter as the planet Neptune. But when astronomers measured its gravitational tug, they received a profound shock. This planet is not a lightweight gas giant. It possesses over 40 times the mass of our entire Earth. That makes it astonishingly dense, a celestial cannonball of unimaginable weight. For a planet of its size, that much mass means it cannot be built like Neptune, with a small rocky core swaddled in a thick, fluffy envelope of hydrogen and helium. The numbers tell a different story. They point to a world made almost entirely of rock and metal, a bare, exposed planetary core. This is the skeleton of a gas giant, a colossal sphere of iron, nickel, and silicate rock that should have been buried under tens of thousands of miles of atmosphere. So where did its gaseous shroud go? How does a planet lose its entire identity? The leading theories are as violent as they are fascinating. One possibility is a cataclysmic collision in the system's early history, a head-on impact with another protoplanet so immense that it blasted away the entire primordial atmosphere in a single, apocalyptic event, leaving the shattered core to continue its lonely orbit. Another, more gradual explanation mirrors what we see at GJ436b, but on a far more extreme scale. Perhaps TOI 849b migrated too close to its star during its formation, and the stellar radiation was so intense, so relentless, that it vaporized and stripped away the entire gaseous envelope over billions of years, like a cosmic sandblaster peeling away a planet's skin layer by layer until only the dense bone remains. There is even a third, more speculative idea, that this world never managed to gather a significant gas envelope at all, perhaps because it formed late in the disk's life when most of the hydrogen and helium had already dissipated. But the sheer amount of heavy material present makes this a less likely story. TOI 849b is a planetary fossil, a direct glimpse into the heart of a giant that we could never otherwise see. It forces us to confront the turbulent, often destructive processes that shape planetary systems long after they form, and it asks a haunting question: if this is the core of a former giant, how many other stripped skeletal worlds are silently circling their stars, the ghosts of planets that once were? The exposed, metallic heart of a world like TOI 849b shows us the brutal aftermath of stellar fury, but our next destination is a planet still very much in the throes of its own incineration. WASP 189b is an ultra-hot Jupiter that redefines the word extreme. Orbiting its blue-white star in a dizzyingly fast 2.7 days, this world is a study in atmospheric violence. Its permanent dayside is a cauldron of light and heat, with temperatures soaring to a staggering 3,200 degrees Celsius. That is not just hot enough to melt steel, it is hot enough to vaporize titanium, one of the most refractory metals known. For years, the composition of this searing atmosphere was a mystery, its spectra a chaotic blur of superheated elements. But recent observations with the espresso instrument have pulled a stunning signature from the glare, the chemical fingerprint of titanium oxide. On Earth, titanium oxide is a brilliant white powder used in paints and sunscreens for its exceptional ability to reflect and scatter light. In the upper atmosphere of WASP 189b, this exotic compound exists not as a powder but as a vapor. And as this vapor is carried by supersonic winds into the slightly cooler margins of the dayside, it could condense into something astonishing: clouds. Not clouds of water or even silicate, but clouds of titanium oxide. These would be highly reflective, metallic clouds, acting like a celestial mirror, bouncing a significant portion of the star's ferocious light back into space. This creates a fascinating atmospheric dynamic, where the very clouds that form from the star's heat might also help to regulate it, creating a complex and alien climate system within the inferno. Adding to its bizarre nature, WASP 189b does not follow a sedate equatorial path. Its orbit is dramatically tilted, almost perpendicular to its star's rotation. From our perspective, this means the planet appears to orbit over the poles of its star, a highly unusual configuration that suggests a violent past. This world was likely not born in this searing close orbit, but was instead thrown here by a gravitational encounter with another massive body, a cosmic game of billiards that left it trapped in this extreme, lopsided dance. WASP 189b is a world of impossible heat and improbable chemistry, where the ingredients for sunscreen form reflective shields in a permanent stellar hurricane, a testament to the universe's capacity for crafting beauty even within the most unrelenting furnaces. Reflective clouds of a different kind cloak another world of profound lightness. Kepler 7b is a gas giant that defies simple classification, a planet so inflated it has earned the label a superpuff. It orbits a star slightly larger and hotter than our own, completing a year in less than 5 Earth days. While not the fluffiest world we have encountered, its density is remarkably low, a fraction of Jupiter's. But its true claim to fame is not its puffiness but its unparalleled shine. Kepler 7b is one of the brightest exoplanets ever detected, reflecting a staggering amount of its star's light back into space. From a distance, this world would gleam like a brilliant, pale marble against the black velvet of space. This extraordinary reflectivity, or albedo, puzzled astronomers for years. What could possibly be so bright? The answer lies in its permanent cloud deck. Using data from the Spitzer and Kepler space telescopes, scientists performed a remarkable feat. They created the first rough cloud map of an exoplanet. By observing how the planet's brightness changed as it orbited its star, going through phases like our moon, they could infer the distribution of clouds across its atmosphere. The data revealed that the western hemisphere of Kepler 7b is dominated by incredibly bright, high-altitude clouds, likely composed of silicates or metallic compounds like vaporized rock and iron. These are not the soft water vapor clouds of Earth, but permanent, scorching mirrors hanging in the sky. The eastern hemisphere, in contrast, appears clearer and darker. This stark asymmetry creates a world with a permanent bright side and a dim side, a global weather pattern locked in place by powerful, stationary jet streams. Yet the mystery of its brightness deepened further. Some researchers noted that the light curve, the dip in starlight as the planet transits, had subtle anomalies. Could there be another structure beyond clouds contributing to that brilliant reflection? A fascinating, though still speculative, hypothesis emerged. What if Kepler 7b possesses a colossal ring system, one that would dwarf the majestic rings of Saturn? A vast, thin disk of highly reflective ice and dust particles orbiting the planet could scatter an immense amount of starlight toward us, explaining the extreme albedo. While the cloud map remains the leading explanation, the ring idea persists because it is so difficult to rule out entirely. The dance of light we observe, the phase variations and transit signatures, is a complex code. Deciphering it tells a story of atmospheric dynamics, of how heat is transported from the scorching day side to the cooler night side, and how that process condenses exotic materials into permanent, shining veils. Kepler 7b is a lesson in reading planetary character from a flicker of distant light, proving that even a featureless point of brilliance can reveal a world of intricate alien meteorology. While some planets cloak themselves in reflective clouds or metallic haze, another offers a rare and perfect clarity. WASP 96b is a hot Saturn, a gas giant orbiting so close to its sun-like star that its atmosphere broils at over 1,000 degrees Celsius. Yet, for all its heat, this world holds an extraordinary distinction. It is almost completely cloudless. Most hot Jupiters and Saturns are shrouded in high-altitude hazes of sodium or silicate dust. Their atmospheres are uniform, featureless blur to our telescopes. But when WASP 96b passed in front of its star, the light filtering through its atmospheric rim told a different story. The data from the Very Large Telescope revealed a spectrum of breathtaking cleanliness, a chemical fingerprint with none of the broad, smeared-out features that indicate clouds or haze. Instead, the signature was sharp, precise, and unmistakable, the clear, deep absorption lines of sodium and, more importantly, the spectral signature of water vapor. This was the first time astronomers had ever detected an exoplanet atmosphere so pristine, so utterly free of obscuring clouds that they could see the water signal with crystal clarity. The sodium signature itself was a revelation, appearing as a perfect textbook example of what scientists had predicted but never cleanly observed. It confirmed that we were looking straight through a vast, transparent envelope of gas, all the way down to the deep, pressurized layers of the atmosphere. Under the intense glare of its star, this clear, scorching sky might even perform a subtle magic. The water molecules in the upper atmosphere, excited by the stellar radiation, could release that energy as a faint, specific glow. This isn't a visible light to our eyes, but in the infrared spectrum, the atmosphere of WASP 96b could literally be glowing with the spectral fingerprint of water, a soft, ethereal emission born from heat and atomic vibration. For scientists, this world is more than just another hot gas giant. It is a pristine laboratory. That cloud-free window allows them to measure the atmospheric composition with unprecedented accuracy, to gauge the abundance of water, sodium, potassium, and other elements, and to begin mapping the vertical structure of the atmosphere itself. It provides a benchmark, a clear standard against which to compare the murkier, cloudier atmospheres of other worlds. WASP-96b proves that sometimes the most valuable discoveries are not about what is present, but about what is absent, a missing shroud that grants us our clearest view yet into the soul of a distant world. A clear sky offers a perfect window into a world's composition, but what happens when the star itself undergoes a fundamental transformation? Orbiting the smoldering ember of a dead star 280 light-years away is a survivor of cosmic proportions, a planet known as WD 1856+534b. This is not a world orbiting a familiar Sun-like star, but a white dwarf, the exposed, Earth-sized core of a star that has already lived and died. The white dwarf is the final, ultra-dense remnant of a star once similar to our own Sun, after it has expelled its outer layers in a beautiful but violent planetary nebula. This leftover core is incredibly hot and small, only about 40% larger than Earth, yet it retains roughly half the mass of our Sun, crushed into that tiny volume. And around this stellar corpse, completing an orbit every 1.4 days, swings a gas giant planet roughly the size of Jupiter. Its existence is a profound, baffling mystery. The star's death throes, when it ballooned into a red giant hundreds of times its original size, should have been an apocalyptic event for any planet in a close orbit. The outer layers of the dying star would have engulfed and vaporized entire worlds, swallowing them whole. For this planet to be where it is today, so close to the white dwarf, it had to have been born much farther out, in the calm, cold suburbs of the original star system. So how did it get here? The leading theory is a story of gravitational chaos and a desperate migration. As the central star began to die and expand, its gravitational influence weakened. This likely destabilized the orbits of other planets in the system, perhaps a second giant planet. Their gravitational dance could have sent WD 1856b spiraling inward on a long, elliptical death plunge. Normally, such a journey would end with the planet being torn apart by tidal forces or consumed, but the physics of the expanding star may have provided a strange salvation. As the star shed its outer layers, it lost a tremendous amount of mass. This mass loss would have caused the orbits of all surviving planets to widen. Astronomers theorize that WD 1856b's inward spiral and the star's own outward push on planetary orbits may have coincided in a delicate balance, allowing the planet to settle into a stable, close orbit only after the red giant phase had completely subsided and the white dwarf was all that remained. It is a celestial ballet of timing and chaos, a game of gravitational pinball where the planet ricocheted through a dying system and somehow found a parking spot next to the ashes. This discovery is monumental because it proves that planets can not only survive the death of their star, but can end up in orbits we never thought possible. It forces us to rewrite the final chapters for planetary systems, including our own. Billions of years from now, when our Sun exhausts its fuel and balloons into a red giant, it will likely vaporize Mercury, Venus, and probably Earth. But the outer planets Jupiter, Saturn, Uranus, and Neptune may yet persist in a widened, colder orbit, and perhaps through their own gravitational interactions, one of them could be sent on a similar journey to one day circle the glowing cinder of our Sun's white dwarf core, a silent witness to the long-vanished inner solar system. WD 1856b is a ghost from a system's past, a testament to the enduring, chaotic life of planets even after their sun has gone out. Survival in the ashes of a dead star is a testament to cosmic endurance, but our next discovery finds a world being forged anew in the fires of its own core. Far from the silent white dwarf, a small, cool star named LP 791-18 hosts a compact family of at least 3 planets. The outermost of these, a world designated LP 79118d, is a rocky planet roughly the size of Earth. On paper, it should be a frozen wasteland. It orbits beyond the system's traditional habitable zone, the region where starlight alone could keep water liquid on the surface. But this world is anything but inert. Data from the Spitzer Space Telescope and TESS revealed something extraordinary. The planet's brightness shows irregular, significant fluctuations over time. These are not the predictable dips of a transit, but spontaneous flares of infrared light, the telltale signature of immense heat radiating from the planet itself. The most compelling explanation for this internal furnace is not a distant sun, but the relentless gravitational tug of war with its celestial siblings. The two inner planets, particularly a massive mini-Neptune, exert a powerful and rhythmic pull on LP 79118d as they all orbit. This constant squeezing and stretching, known as tidal heating, flexes the planet's interior like a ball of clay being kneaded. That friction generates tremendous heat from within, potentially enough to melt rock and drive global volcanic activity on a scale that dwarfs anything in our solar system. Imagine a world where the ground itself is a thin, brittle crust over a churning magma ocean, punctured by countless volcanoes spewing lava and gases into a thin atmosphere. This continuous resurfacing could create a dynamic young geology, reminiscent of Jupiter's moon Io but on a planetary scale. Yet here lies the breathtaking possibility. All that volcanic activity and internal heat might be doing more than just creating a fiery landscape. Scientists theorize it could be maintaining a stable, global ocean, not on the surface but beneath a thick shell of ice. The heat from below would melt the base of the ice layer, creating a vast, dark subsurface sea, insulated from the frozen void of space above. On Earth, we find ecosystems thriving in the complete darkness of deep-sea hydrothermal vents, powered not by sunlight but by chemical energy from the planet's interior. LP 79118d could offer precisely that environment on a planetary scale, a world warmed from within, with volcanic vents on a seafloor potentially providing the chemistry and energy needed for life to arise. This redefines the very concept of a habitable world. It tells us that a planet does not need to bask in the golden light of a sun to be alive. It can generate its own warmth, its own dynamism, from the gravitational dance it shares with its neighbors. If life exists in that dark, subsurface ocean, it would be a form utterly alien to our sunlit experience, a biosphere born from tidal rhythms and volcanic fire, forever hidden beneath a ceiling of ice. A world of solid rock can be far more massive than we ever dared to dream. In the constellation Draco, orbiting a star 11 billion years old, a planet named Kepler 10c completes a 45-day orbit. When it was first measured, its size alone was staggering. It was over twice the diameter of Earth, classifying it as a mini-Neptune. But when astronomers used ground-based observatories to weigh this giant, the data delivered a shock that reverberated through the field. This planet possessed 17 times the mass of our entire world. For a planet of that volume, such a colossal weight meant only one thing, an almost impossibly high density. Kepler 10c was not a puffy gas dwarf. It was a solid sphere of rock and metal, a true rocky planet on a monstrous scale. It earned the immediate nickname, the Mega-Earth. This discovery shattered a fundamental assumption in planetary science. The prevailing theory held that once a rocky planet grew beyond about 10 Earth masses, its gravity would become so strong during formation that it would act like a cosmic vacuum cleaner, voraciously sucking up all the hydrogen and helium gas from the surrounding protoplanetary disk, inevitably ballooning into a gas giant like Neptune or Jupiter. Kepler 10c defied that rule completely. Here was a world 17 times our mass, built like a scaled-up version of Earth with no significant gaseous envelope. It proved that the universe has more than one recipe for building planets. Somehow, in that ancient disk of material around its star, Kepler-10c gathered an immense amount of heavy elements, rock and iron, but it either formed late after most of the light gas had dissipated, or it formed in a region of the disk that was unusually rich in rocks and metals and poor in hydrogen. Its very existence opened up a new category of planet, the massive terrestrial world. Imagine the geology of such a place. The surface gravity would be crushing, nearly 3 times stronger than Earth's. A simple walk would feel like carrying another person on your back, and any mountain range would be pressed down under its own immense weight, leading to vast, smooth plains and low, worn-down hills. The internal pressure would be so extreme that the minerals in the mantle could form exotic, high-density crystals unseen on our world. Yet, the most profound implication of Kepler-10c is not its present but its past. This planet orbits a star that formed less than 3 billion years after the Big Bang. In that early, primordial universe, heavy elements like silicon, iron, and magnesium, the very building blocks of rocky planets, were far more scarce. Finding a mega-Earth from that epoch suggests that the cosmic kitchen started cooking rocky worlds, and cooking them big much earlier than anyone thought. It tells us that the ingredients for terrestrial planets were available almost as soon as the first generations of stars lived, died, and seeded the galaxy with the ashes of their explosions. If such a massive, ancient rock could form and survive, it forces us to ask what other kinds of durable, long-lived worlds are waiting in the oldest reaches of the galaxy, silent witnesses to nearly the entire history of the cosmos. But even the most orderly migration cannot explain a world that seems to defy the very spin of its star. WASP-17b is a gas giant that moves with a profound sense of cosmic rebellion, orbiting in the exact opposite direction of its star's rotation. This is a retrograde orbit, a celestial dance performed entirely backwards. In our own solar system, every planet orbits the Sun in the same direction it spins, a legacy of the swirling disk of gas and dust from which they all formed. This prograde motion is the cosmic norm, the expected outcome of a system born from a single spinning cloud. WASP-17b shatters that expectation. Its orbit is not just tilted, it is completely flipped, like a car driving the wrong way on a planetary freeway. This discovery sent shockwaves through the field of planetary science because it directly challenged the standard model of how hot Jupiters form. The prevailing theory suggested these giants formed far out and then migrated inward smoothly through interactions with the protoplanetary disk. That process should have preserved their original prograde direction. A retrograde orbit is a glaring sign of violence, a scar from a gravitational catastrophe that occurred long after the planet's birth. So what could possibly flip an entire world? The leading suspect is a gravitational showdown, a close encounter of astronomical proportions. In the system's chaotic youth, WASP-17b may have had a massive sibling, another giant planet. Their gravitational tug-of-war could have sent them into a destabilizing dance, pulling each other into wildly eccentric, intersecting orbits. During one perilously close pass, the gravitational slingshot effect could have been so extreme that it literally turned WASP-17b's orbit inside out, reversing its direction and hurling it into its current, searingly close path around the star. Another, even more dramatic possibility involves a stellar intruder. A passing star not bound to the system could have wandered too close. The gravitational influence of this foreign sun could have yanked on the planet, violently perturbing its orbit and sending it into a retrograde spin. This world is a permanent monument to a past of celestial billiards, a game where the planets themselves were the balls. The implications are profound. WASP-17b tells us that some planetary systems do not evolve in quiet isolation. Their histories can be written in collisions, near misses, and stellar flybys that completely rewrite a planet's destiny. It forces astronomers to consider that the calm, ordered architecture of our solar system might be the exception, not the rule, and that the true story of many exoplanets is one of chaos survived, a path set not by gentle formation but by ancient gravitational warfare. The gravitational chaos that flips entire orbits pales before the profound, silent cold of true cosmic isolation. Drifting alone through the void, a mere 7.4 light-years away, is an object known as WISE 0855-0714. It is not orbiting any star. It is a solitary wanderer, a dark, frozen ember adrift in the interstellar night. Discovered by the Wide Field Infrared Survey Explorer, its most shocking feature is its temperature, a bone-chilling -23 degrees Celsius. That is colder than a winter day at the Earth's North Pole. For an object glowing with its own residual heat, that is astonishingly frigid. This temperature places it in a mysterious category, somewhere between the largest planets and the smallest failed stars. It is classified as a brown dwarf, a substellar object too small to ignite the sustained nuclear fusion that powers a true star. But WISE 0855 is an extreme even among brown dwarfs, one of the coldest and faintest ever detected. Its feeble warmth comes only from the leftover gravitational energy of its formation, slowly leaking away into the infinite cold of space. What makes this lonely wanderer so fascinating to planetary scientists is its atmosphere. Detailed infrared spectroscopy has revealed a stunning truth. Its thin shroud of gases contains clouds, not of ammonia or methane like on Jupiter, but of water, water ice, and water vapor. This gives it a familiar yet deeply alien meteorological profile. It likely possesses a banded atmosphere with jet streams and storm systems, but all driven by the faint internal heat of a cooling ember under a permanent starless black sky. The debate over its classification cuts to the very heart of how we define a planet. Is it a rogue planet, a giant world like Jupiter that was violently ejected from its home solar system during some ancient gravitational upheaval? Or is it a brown dwarf that formed in isolation like a star from a collapsing cloud of gas that simply wasn't massive enough to shine? The line is blurry, and WISE 0855 sits directly on it. Its mass is estimated at between 3 and 10 times that of Jupiter, squarely in the overlap zone where the largest planets and the smallest brown dwarfs meet. This lonely object reveals a hidden population of such dark, nomadic worlds. Previous surveys suggest these free floaters may be incredibly common, perhaps outnumbering stars in our galaxy. They are the ghosts of planetary systems, either born alone or exiled, forever traveling the dark roads between the stars. Studying the faint infrared glow of WISE 0855 is like trying to read by the light of a match held miles away, but it offers a priceless glimpse into the atmospheric physics of a world without a sun. It shows us that complex weather with water clouds and circulating gases can exist entirely independent of stellar warmth, powered solely by the deep, slow cooling heart of a world itself. If such a frozen, solitary nomad can have a dynamic atmosphere, what other forms of isolated, internal weather might be unfolding in the endless dark on countless other unseen wanderers? The profound loneliness of a drifting brown dwarf stands in stark contrast to a world caught in the gravitational web of not one, but 3 suns. In the constellation Cygnus, a Saturn-sized planet named KY5b exists within a stellar family portrait of staggering complexity. This world orbits the primary star in a hierarchical triple-star system, a celestial arrangement where 2 stars, KY5b and c, dance closely together as a binary pair, while they both, in turn, orbit the main star KY5a at a much greater distance. The planet itself circles that primary star, KY5a, but its path is anything but simple. When the Kepler mission first flagged it as a potential planet candidate in 2009, the signal was messy and confusing. The data was so convoluted by the gravitational influences of the other 2 stars that astronomers essentially set it aside for a decade. a tantalizing puzzle deemed too difficult to solve with the tools of the time. It was not until the advent of more powerful ground-based telescopes and advanced analytic techniques that the truth of KY5b was finally pulled from the noise. The confirmation revealed a bizarre orbital misalignment. The planet does not orbit in the same plane as the primary star's equator, which is common. More strangely, its orbital plane is also tilted relative to the orbit of the distant binary pair of stars. This means the planet's path is skewed, a tilted ring that seems to ignore the overall spin of its own stellar family. How does a planet end up on such a slanted, seemingly disobedient trajectory? The likely story involves a dramatic gravitational tug-of-war during the system's infancy. As the three stars and the protoplanetary disk of gas and dust swirled together, the gravitational pull from the binary stars KY5b and C could have yanked on the disk surrounding the primary star. This pull would have warped the disk, tilting it. The planet then formed within this already slanted construction zone, inheriting its crooked orbit. Another possibility is that the planet formed in a normal, flat disk, but the gravitational influence of the binary stars later perturbed its path, slowly pulling it into its current misaligned state over millions of years. This world offers a masterclass in celestial dynamics, proving that planets can form and persist in some of the most gravitationally crowded neighborhoods imaginable. From the surface of a hypothetical moon, the sky would be a constantly shifting masterpiece. The primary sun, KY5a, would dominate the day, but the distant binary pair would also be visible, two bright points of light that change their separation as they orbit each other, sometimes appearing as a single brilliant star, other times as a distinct duo, all while slowly wheeling across the heavens. KY5b is a testament to the universe's love of complex patterns, a world whose very existence and strange tilt were only revealed after a decade-long detective story, proving that some planetary mysteries require patience, better tools, and a willingness to revisit the cosmic cold cases. That search for life in alien oceans leads us to one of the most tantalizing discoveries of our time, a world named K218b. Orbiting a cool red dwarf star 120 light-years away, this planet is not a rocky twin of Earth. It is a mini Neptune, a world about 2.6 times the size of our own, with a mass over 8 times greater. For years, such planets were written off in the search for life, assumed to be either small gas giants with crushing pressures or icy worlds with thick, inhospitable atmospheres. But K218b resides squarely within its star's habitable zone, and recent observations have completely rewritten its story. Using the Hubble Space Telescope, astronomers performed a meticulous analysis of the starlight filtering through the planet's atmosphere during multiple transits. The data revealed an unmistakable and breathtaking signature, the spectral fingerprint of water vapor. This alone was monumental, the first detection of water in the atmosphere of a habitable zone exoplanet. But the deeper analysis hinted at something even more extraordinary. Within the noisy data, researchers also identified potential traces of methane and carbon dioxide, and most controversially, a tentative signal for dimethyl sulfide. On Earth, dimethyl sulfide is a gas produced almost exclusively by biological processes, specifically by marine phytoplankton. It is considered a strong potential biosignature, a chemical flag that could signal the presence of life. This combination of findings propelled K218b into the spotlight and gave rise to a revolutionary new planetary concept, the Hycean world. Hycean, a portmanteau of hydrogen and ocean, describes a hypothetical class of planets with a specific architecture, a massive, hydrogen-rich atmosphere enveloping a global, planet-wide liquid water ocean. Under the immense pressure of such a thick atmospheric blanket, the ocean could remain liquid even at surface temperatures far higher than Earth's, and the hydrogen atmosphere itself could act as a powerful greenhouse, trapping enough heat to maintain those conditions even around a faint red dwarf star. This model perfectly fits the data we have for K218b. It suggests a world utterly alien to our experience. The sky would not be blue, but a perpetual hazy orange or pink due to the hydrogen and possible hydrocarbon hazes. The atmospheric pressure at the ocean's surface would be dozens or even hundreds of times greater than Earth's, more akin to the crushing depths of our own abyssal trenches. There would be no land, no horizon, just an infinite steamy sea meeting an oppressive, dense sky. Storms of unimaginable scale might churn this global ocean, and the dim red sun would be a permanent, blurred fixture in the haze. The potential detection of dimethyl sulfide, while still unconfirmed and requiring verification from the more powerful James Webb Space Telescope, is what transforms K218b from a fascinating oddity into a groundbreaking target. It raises a profound question: could life exist not on a rocky Earth-like planet, but in the global ocean of a hydrogen-shrouded water world? Could biological processes thrive in a super-pressured, hot ocean beneath an alien sky? The Hycean world concept dramatically expands the cosmic real estate where we might search for life, suggesting that some of the most promising habitats may look nothing like our pale blue dot, but instead resemble a steamy, shrouded aquatic globe. K218b is now a prime target for the next generation of telescopes, a world that may hold the first whisper of life beyond our solar system, not on a twin of Earth, but in a realm we are only beginning to imagine. The possibility of life in a shrouded water world is a whisper of biology, but the next planet on our list roars with the pure, unadulterated physics of an atmosphere pushed to its breaking point. WASP-121b is an ultra-hot Jupiter so intensely scorched that its atmosphere is literally boiling away into space, much like the ill-fated GJ436b. But this world holds an extra layer of complexity, a discovery that seemed to defy the basic rules of atmospheric science. Here, astronomers confirmed the existence of something we thought impossible in such a hellish environment, a stratosphere. On Earth, our stratosphere is the layer above the weather where temperature increases with altitude, thanks to the ozone layer absorbing the sun's ultraviolet radiation. It creates a stable, warm ceiling. On a planet like WASP-121b, orbiting so close its star that its upper atmosphere exceeds 2,500 degrees Celsius, scientists expected temperatures to simply decrease the higher you went as the star's heat faded with distance. But observations from the Hubble Space Telescope revealed the opposite. By studying the infrared glow of specific molecules in the planet's atmosphere as it passed behind its star, a technique called secondary eclipse spectroscopy, researchers made a startling find. They detected the signature of water molecules, but these weren't just absorbing light, they were glowing, emitting infrared radiation. That glow is the crucial clue. For water molecules to emit that strongly, they must be even hotter than the layers of gas below them. This meant the temperature was increasing with altitude, a definitive sign of a stratospheric layer. So what could possibly act as a sunscreen on a world this violent? The answer lies in exotic chemistry. Further analysis pointed to the likely culprits: titanium oxide and vanadium oxide. These metallic compounds, present as vapor in the upper atmosphere, are voracious absorbers of ultraviolet and visible light from the star. Just as Earth's ozone layer soaks up UV light to heat our stratosphere, these metallic vapors absorb the ferocious stellar radiation on WASP-121b. They act like a celestial heat trap, capturing immense energy high in the sky and re-radiating it, superheating the upper atmosphere to create that inverted temperature profile. This creates a bizarre atmospheric structure. Imagine a world where the upper skies are actually hotter than the lower ones, where the very concept of heat rising is turned on its head by the presence of metallic sunscreens in the air. This discovery was more than a planetary oddity, it was a fundamental validation. It proved that the physical processes that create atmospheric layers are universal, even if the chemicals involved are utterly alien. The presence of a stratosphere on WASP 121b tells us that no matter how extreme the environment, atmospheres can organize themselves into structured, predictable layers, governed by the interplay of starlight and chemistry. It provides a critical reference point for understanding the climate of every other exoplanet, showing that the principles we know can apply in the most unexpected places, even in the blistering glow of a world being slowly vaporized by its sun. The intricate atmospheric layers of a boiling giant reveal a universe governed by universal physical laws, yet some of the most profound order exists not within a single world, but in the perfect harmony of an entire family. 39 light-years away, a faint, cool red dwarf star named TRAPPIST-1 hosts a solar system that has rewritten the rules of planetary architecture. Around this quiet sun orbit not one or two, but 7 rocky planets, each roughly the size of Earth or slightly smaller. This alone is a staggering discovery, a compact family of terrestrial worlds. But the true wonder lies not in their number, but in their motion. These 7 sisters are locked in an exquisite gravitational embrace known as a resonant chain. Their orbital periods, the length of their years, are tied together in near-perfect mathematical ratios. For every 8 orbits the innermost planet completes, the second planet completes 5. For every 5 orbits of the second, the third completes 3. This precise pattern continues out through the system, a celestial symphony of clockwork precision. It means the planets regularly tug on each other in a gentle, predictable rhythm, their gravitational influences aligning at specific points in their orbits to keep the entire system stable over billions of years. This delicate dance prevents catastrophic collisions or ejections, maintaining the harmony of this crowded neighborhood. From the surface of one of these worlds, the sky would be a constantly shifting tapestry of neighboring planets. They would appear not as mere points of light, but as distinct, visible disks, some larger than our full moon, passing each other in a slow, stately ballet governed by an unbreakable cosmic rhythm. Several of these planets, particularly TRAPPIST-1e, F, and G, orbit within the star's habitable zone, that temperate region where liquid water could pool on a rocky surface. Given their Earth-like sizes and compositions, they represent some of the most promising targets in the search for life beyond our solar system. But the true gift of the TRAPPIST-1 system is the unparalleled opportunity for comparative planetology. For the first time, we can study 7 sibling worlds, all born from the same stellar nursery around the same star, yet each occupying a slightly different environment. By comparing their atmospheres or lack thereof, we can begin to answer fundamental questions. Why does one world retain a thick atmosphere while another is stripped bare? How does the intensity of stellar flares from the red dwarf parent star affect each planet differently? If signs of chemistry suggestive of life appear on one world but not its neighbors, the contrast would be incredibly revealing. This system is a controlled experiment on a galactic scale, offering a chance to understand the factors that make a planet living or dead, shrouded or barren. It transforms our search from examining solitary, distant points of light to reading an entire chapter of planetary evolution written across 7 different pages, each one influencing the story of the others through their timeless, resonant dance. That resonant dance of 7 rocky siblings reveals a planetary system in perfect gravitational harmony, but some worlds are born from chaos so profound it leaves its mark in the very air they breathe. Orbiting the young, brilliant star HR 8799, a gas giant named HR 8799e is a world seen not as a flicker of starlight, but directly as a distinct blazing point in telescope images. This is a rare and precious glimpse, like seeing a planet in a family portrait rather than just hearing its footsteps. It is a colossal world, several times the mass of Jupiter, and it is still an infant in cosmic terms, only about 30 million years old. Its youth is its defining feature, for it glows with the fierce, leftover heat of its violent birth, radiating a sullen orange-red light like a cooling ember plucked from a stellar forge. This intrinsic glow is what allows us to see it directly, and by carefully dissecting that light into a spectrum, astronomers have performed a chemical autopsy of its atmosphere from trillions of miles away. The results were shocking. The atmosphere of HR 8799e is not a balanced mix of familiar gases. Instead, it is choked with carbon monoxide, a simple molecule of one carbon and one oxygen atom. In a stable, quiescent atmosphere around a gas giant, chemical reactions over time should convert much of that carbon monoxide into methane. Yet, the expected methane is conspicuously, almost completely absent. This chemical imbalance is a glaring anomaly, a sign that something is violently preventing the atmosphere from settling into equilibrium. The leading explanation points to a history of unimaginable violence, not in the sky but deep within the planet itself. The intense heat still radiating from HR 8799e suggests its interior is a churning, turbulent cauldron. This internal fury could be driving powerful vertical winds, massive convection currents that dredge up carbon monoxide-rich gas from the scorching depths and blast it high into the observable atmosphere faster than it can chemically change into methane. It is a planet with its guts turned inside out, its deep chemistry exposed by relentless internal storms. But there is another, even more dramatic possibility. This atmospheric strangeness could be the lingering scar of a cataclysm. In the chaotic early days of the system, HR 8799e may have suffered a head-on collision with another massive protoplanet, an impact of such staggering force that it completely remixed the planet's interior. Such a collision would have released titanic energy, superheating the atmosphere and violently stirring the chemical pot, resetting its composition and perhaps even stripping away layers of methane that had begun to form. The overabundance of carbon monoxide we see today could be the direct fallout of that ancient crash, a chemical fossil of planetary birth by catastrophe. This world teaches us that a planet's atmosphere is not just a blanket, it is a history book. The molecules in its air record the events of its youth, whether that story is one of serene, internal churning or of a single, shattering blow that defined its entire existence. HR 8799e, glowing fiercely in the void, offers a sobering lesson. Some of the most majestic giants in the galaxy may carry the chemical scars of their most brutal childhood moments. While many worlds suffer under the constant glare of their suns, one planet endures a seasonal cycle of pure atmospheric torture. HD 80606b is a gas giant, a so-called warm Jupiter, but its orbit is a masterpiece of celestial extremes. This world does not trace a gentle, circular path. Instead, it follows a wildly elongated ellipse, a cosmic roller coaster that subjects it to the most dramatic temperature swings imaginable. For most of its 111 Earth Day year, HD 80606b drifts in the cold, silent outer reaches of its system, a frigid giant under a dim, distant sun. But then the plunge begins. Gravity pulls the planet into a dizzying, weeks-long dive toward its star. As it approaches the closest point of its orbit, known as periastron, the star grows from a faint point to a blazing disk filling the sky. In a matter of hours, the surface temperature on the planet's dayside skyrockets. It goes from a bitter negative 73 degrees Celsius to a searing 1,227 degrees, a spike of over 1,300 degrees in less than a single Earth day. This is not gradual warming, it is a planetary flash heating event of almost unimaginable violence. The atmosphere cannot cope with such a sudden, brutal influx of energy. The result is a global shockwave. The superheated air on the permanent dayside expands explosively, triggering supersonic winds that scream across the Terminator line at speeds exceeding 18,000 kilometers per hour. These winds are not gentle breezes, they are planet-circling hurricanes of superheated gas, carrying enough thermal energy to literally rock the entire world. Astronomers using the Spitzer Space Telescope have actually watched this happen. They observed the planet's infrared glow, its heat signature, intensify 1,000-fold in those critical hours around closest approach before fading again as the world swung back out into the cold. The data suggests the heating is so rapid and intense that it creates a propagating shock front, a wall of heat and pressure that races ahead of the actual rotation of the planet, stirring the entire atmosphere into a frenzied global storm. Then, as quickly as it arrived, the planet whips around the star and begins its long journey back into the deep freeze. The atmosphere, now pumped full of heat, must radiate that energy away into space. The temperature plummets once more, and the furious storms subside into a slower, colder churn, until the next close approach reignites the cycle. HD 80606b is a unique natural laboratory. Its extreme, predictable orbit allows us to watch atmospheric physics in fast forward, to see how a global climate responds to a sudden, catastrophic injection of energy. It shows us that a planet's weather is not just about where it is, but about the path it takes to get there and how violently that path can change. This world lives a double life, a quiet ice giant for most of the year, and a brief, screaming inferno for a few terrible days, a testament to the dramatic stories written in the elliptical paths of wandering giants. Our final destination is not a world orbiting a star, but a solitary wanderer that lights up the darkness from within. In the silent void between constellations, a massive object known as SIMP J0 1365663 plus 0933473 drifts alone. It is a rogue planetary mass object, a body with about 12 times the mass of Jupiter, untethered to any sun. It is cold, faint, and by all rights should be invisible to us. Yet it screams its presence across the light years with a voice of pure magnetism. This lonely giant possesses a magnetic field 200 times stronger than Jupiter's own immense magnetosphere. And that field is alive with activity, generating colossal, permanent auroras that crackle across its polar skies. We detected this world not by the light it reflects, but by the powerful, pulsing radio emissions its magnetic activity broadcasts into space. These are the same kind of radio waves generated by Jupiter's auroras, but from a planet with no star to provide a solar wind. So what powers these brilliant light shows in the absolute black? The energy must come from the object itself. The leading theory points to its interior, a churning, convective dynamo of metallic hydrogen and helium, driven by the immense gravitational pressure and the slow, relentless heat left over from its formation. As this electrically conductive fluid moves within the object's deep layers, it generates that monstrous magnetic field, which in turn accelerates charged particles toward the poles, where they slam into the thin atmospheric gases and ignite the auroras. This makes SIMP a priceless natural laboratory. Studying this lonely, magnetic beacon allows us to understand the interior dynamics of gas giants in a pure, isolated state. There is no blinding glare from a nearby star to obscure our view, no complicating stellar winds or radiation to muddy the data. We are seeing the intrinsic heart of a giant, its internal engine laid bare by the radio whispers it sends into the void. This discovery reveals that powerful magnetic personalities are not exclusive to stars or orbiting planets. They can belong to the nomads as well. It suggests that countless such dark, magnetic wanderers could be drifting unseen through our galaxy, each carrying within it the fading heat and churning metal of its birth, painting its own lonely skies with silent, spectacular light. This gallery of alien worlds reveals a cosmos far stranger than we ever dared to dream. From a planet where it rains molten iron to another that is darker than coal, from a world that is a single global ocean to the exposed core of a former giant, each discovery shatters an old assumption. These 25 bizarre exoplanets are not merely curiosities, they are fundamental revisions to the textbook of planetary science. They prove that our own solar system is just one quiet neighborhood in a galaxy teeming with infinite architectural possibilities. The sheer diversity we have witnessed, from Hycean water worlds shrouded in hydrogen to frozen nomads glowing with their own magnetic light, forces us to abandon any narrow definition of what a planet can be. More profoundly, it expands our imagination for where life might take hold. Habitability is no longer confined to a rocky ball in a sun's golden zone. It could exist in the subsurface ocean of a tidally heated world, or in the perpetual twilight of a locked planet, or even in the deep, pressurized seas beneath a thick alien sky. Every new telescope, every fresh observation peels back another layer of this cosmic mystery, revealing that the universe is not only weirder than we suppose, but weirder than we can suppose. Our journey is just beginning. The next chapter will be written by missions like the James Webb Space Telescope, which is right now analyzing the atmospheres of worlds like K2-18b, searching for those elusive chemical signatures. To stay on this frontier of discovery, all we need is to remain curious. Look up at the night sky and remember that for every point of light you see, there are likely dozens of unseen worlds, each with its own impossible story. We want to hear which of these bizarre planets captured your imagination the most. Was it the diamond world, the iron rain giant, or the lonely magnetic wanderer? Share your thoughts in the comments below, and let's keep exploring the universe's greatest mysteries.